Hi, this is Kevin Trainer. Welcome to my lecture on Chapter 11 of Murach's third edition MySQL book. Chapter 11 is about how to create databases, tables, and indexes. So I'm going to leave, as usual, the objectives for you to read on your own. And here's some more. So, um, let's give a little context, okay? Uh, this chapter is about all of the SQL statements that are needed to create a schema for a database, okay? There's a whole series of them. Typically, one puts them all into a script associated with a database, and you can use it to recreate the database every time you run the script. We, for the most part, are going to learn how to use the statements individually. Okay. Um, so what we're going to do is we're going to, although we'll talk about a script and we'll show you one, and I have some comments about the appropriateness of collecting these all up in a script. For the most part, we're going to learn this a statement at a time. Okay, these are all part of what's called the DDL. Up until now, we've been working with the DML, the data management language. That's a component of SQL. The DDL is the other component of SQL. It's the data definition language. So let's look here. One of the things that you might want to do is create a database. So there's a create database statement. Okay. It has optionally, you can say if not exists. So if you use that, it'll check and see if you already have a database by the name that you provide. In this case, we're calling it a DB name. And if you don't, then it will create one. And if you do, it won't if you use that option. So here are a couple of examples. Create a database AP. I know that on my machine that would create an error because I already have an AP database. Or you could say create database if not exists AP. On my machine, because I have an AP database, I'd get a warning that it didn't create the database because I already had one. Okay. On the other hand, if I went and dropped the schema, if I went into Workbench and over to the left-hand panel where I can deal with the schemas, and I dropped the AP schema, either of them would work. Okay, because I wouldn't already have an AP database. Likewise, we can drop a database. And in fact, I was just talking about dropping a database. So we can say drop database DB names, and this optional if exists will keep you from failing if it's already been dropped, so it's not there. So two possibilities here: drop database AP. That's going to drop it if you have the AP database. If you don't, you're going to get an error. And drop a database if exists AP. Um, if it does exist, it's going to drop it, and you're going to get a successful response. If it doesn't, uh, let's see, if it doesn't exist, it's not going to drop it, but it will show you a warning. Okay. Use DB name. For instance, use AP, or in my class, we've been using this all along. And when we're doing our My Guitar Shop exercises, we've been saying use My Guitar Shop. One of the things that I don't like about the examples we show in this book is that they're not terminated with a semicolon. And the fact is, a lot of the work that we do is going to go into a script. And as soon as you have more than one statement in a script, you need to separate them with a semicolon. So, hang on one second. So, what we do in my class is whatever statement we're using, we end it with a semicolon. Even though the semicolon is officially a separator, we treat it like a terminator, and we put it at the end of every statement that we use. Then we can add other statements and make this a proper script, and the ones that we already have are going to work just as well as they always did. Create table. Okay, so we're going to say create a table. We have an optional prefix of a database name, and then we say table name. Okay, so if we don't prefix it with a database name, it's going to create it in the current database. The way I teach people in my class is, even when we're working in Workbench, that we always use the DB name statement at the top. So if we do that, then it's going to create the table in the database that we're currently using. Okay? And then what goes inside of the create tables, there's a set of parens, and there are a bunch of column specifications. And then at the very end, there are these optional table level constraints. And we're going to learn about all of those. When we define a column, we name the column, and then we give it a data type, and then we give it these optional attributes if they apply. And some of these optional attributes include not null, unique, default, and then a default value, and auto increment. Okay? So here's some examples. The first one, here's a statement that creates a table without column attributes. So we're going to create table vendors. Inside, we're going to specify two columns. Vendor ID, that's going to have the data type int. Vendor name, which is going to be a varchar 50. And you'll notice that the comma is used as a separator in here. Okay, so in this case, we cannot put an extra comma at the end. Okay, that turns out to be a syntax error. Okay, so you can only use a comma as a separator. You can't use it optionally as a terminator, even though it's officially a separator, like we were doing with the semicolon. Okay, so we've created a table here with two columns. Okay, now this is a table that has no primary key. I just want to point out that that's not typical. Can you create a column without a primary key? Yes, you can. Yeah, is it a good practice? No, it's not. We're only doing it here because we haven't gotten to primary keys, how we create a primary key yet. Okay? So the second part, a statement that creates a table with column attributes. So we did the same thing. We're creating table vendors, two columns, vendor ID and vendor name. Okay, they have the same data types. A vendor ID is an int, a vendor name is a varchar 50, but they also have these column attributes. So on vendor ID, the two that we're saying are not null and unique. Okay. Oh, I'm sorry, we're seeing three, and auto increment. Okay. Now, a couple of interesting things here. Uh, Not null is one attribute, even though it's two words. Okay. Um, Unique is one attribute. Auto underscore increment is one attribute. It's probably a good idea. It's probably good at design to put the sort of underscore in between auto and increment so that it appears to be one attribute. Why they didn't do that with not null? I think that not null is from an earlier time than auto increment in terms of the SQL specification. Okay, and then vendor name two optional attributes, not null, unique. Notice how there's only one comma. Okay, so there's only one comma. One that, like in the example before, it separates the column definition for vendor ID from the column definition for vendor name. So even though we have in one case two, in the other case three column attributes, they're not separated by commas. They are separated by white space, and in this case, a pretty flexible amount of white space. And one of the things that we're seeing is a common practice of lining up the column names in a column, the data types in a column, and the attributes in a column. And of course, when we can't fit them all in, we continue and then we go into the column. So auto increment is continued on the next line, but we have indented it in order to put it into this third column. Now, for the server, does the server care if we have this column formatting? No, it doesn't. It's pretty much will interpret one character of space is the same as multiples, and it will interpret a new line as just a space. Okay. Well, why do we format it this way? Well, we format it this way for the human readers of this definition so they can easily find the parts of the definition. And that's why it's a common and also a good practice. Here's another statement that creates a table with column attributes. So create table invoices. So we're doing invoice ID, vendor ID, invoice number, invoice date, invoice total, payment total. And let's see what kind of types we have. Well, the first couples are IDs. Invoice ID is eventually going to be the primary key, so that's just an int. Vendor ID is going to be a foreign key, although we haven't arranged for it to be so yet, so that's an int. Invoice number is a varchar 50. And I'll remind you that this is not our invoice number, but this is the because this is accounts payable. This is the number of the invoice from somebody else. And so characters are important for us because they might have the equivalent of an invoice number, some kind of invoice ID that was alphabetic or a combination of numbers and alphabetics. We have a date. We have two amounts that are decimal 92. Okay, and then we have some attributes. Invoice ID is not null and unique. Vendor ID is not null. Invoice number is not null. The date has no additional attributes. Invoice total is not null. The payment total is default 0. Okay. So when we give it a default, like 0, if in fact we do an insert and we don't provide a value, we provide a null for that, it will be given the default 0. So having a default value implies that it's not going to be left null even if you provide the null value when you do the insert. That's just how that works. And again, I just want to emphasize, because we haven't identified the primary key, this isn't a final version. Okay, this is just some kind of incremental improvement over what we've seen before, but it's not the version we're going to stop on. Okay, now we're going to learn how to create a primary key. So it turns out there are two ways to create a primary key. And we're going to do this at the column level first. Okay, so when you create a primary key, we don't call the phrase that we put on that column at definition. We don't call it an attribute, we call it a constraint. Why do we call it a constraint? Well, generally the things that constrain the values and the behavior of the data in a particular column are called constraints. Unique is called a constraint as well. So one of the things we can do is we can have the name of the column, we can have the data type, and we can just say primary key, and then we can have other column attributes. So here's a vendor's table in which we've used the primary key constraint at the column level. Vendor ID int primary key auto increment. Okay, so one of the things that two attributes that we had seen before that we're not seeing now are unique and not null. Okay, is that to say that even though it's the primary key, we don't want it to be unique and will allow it to be null? No, it turns out that saying that something's a primary key implicitly also says that it has to be unique and it can't be null. Okay, would it be an error to say primary key unique, not null? No, it wouldn't be. It just would be redundant. Okay, so that's the reason why we just have primary key. And now here we've said auto increment, and of course auto increment is a special default value which gives that key the next higher int value that hasn't been used. Okay, then we've got vendor name, varchar 50 not null unique. I don't think we changed that. I think that's the same. So the new thing is the handling of the primary key. Now, I just want to point out what a great design we have here in that the vendor ID is a primary key. It's not allowed to be null. It has to be unique because those are implicit characteristics of primary keys. But the vendor name is also not null and unique. And this has to do with, kind of the relational database way. Okay, a lot of tables, one of the important functions of tables is to be what I call a lookup table, okay? Uh, which means we use them as a target of foreign keys so that we don't have to code text into other tables. Okay, so instead of coding the vendor name in some other table like the invoice, we'll use the vendor ID foreign key to point to the vendor's table where we can pick up the vendor name. But it's important to avoid confusion that the vendor names that you put into lookup tables like vendor, that they not be null and that they not be duplicates. Okay, so this is pretty typical of these lookup kinds of tables that we have a primary key that looks about like we see. And then to the extent that we have a name or a description where we're pretty typically going to include the attributes not null and unique, those are what is going to allow this to be a fully functioning lookup table that allows us to control values. Okay, now the only thing we did on that last one that was new is we did we said that we had a primary key, that the vendor ID was a primary key. And we did that at the column level. Is that the only way to do it? No. Okay. So after we define each of the columns, we're allowed to have these, what we call table level constraints. Okay. So for instance, instead of up on the column where we define the vendor ID column here, instead of saying that it's a primary key, we can just leave that out, and then later, after we've defined all the columns, then come the table level constraints. Here we say constraint, and we give it a name, vendors PK. That's a pretty good name. It's the primary key for vendors. And then we say primary key. And because you have to tell it which of the columns you want to do, then we have in parens vendor ID. Okay. Now, why would you do one of these over the other? Well, for a single column, a primary key, this is a matter of style. Okay. One's not better than the other. They both create a primary key on vendor ID. What's the difference? Not really much. It's a stylistic difference. Okay. The other thing that you can do is that you can create a unique constraint on vendor name. Okay. By saying constraint vendor name UQ unique, and then identify the field vendor name. Okay. Now, again, is that stylistic? Yeah, it's largely stylistic. So if we're trying to create a primary key or a unique constraint on a single column, well, then we can either do it on the column itself, all right, with these constraint names and attributes like we did on the last slide, or we can wait to get down to the bottom of the definition for the table, and we can do it at the table level. Okay, and again, provided that these are on single columns, it's really your choice as to style. Now, when these things that we're trying to constrain are based on multiple columns, then we only have the the option of doing them at the table level. Okay, and I think we're going to see an example of that next. So let's give it a look. Okay, so here we have table invoice line items. Okay, and we're saying that the primary key for invoice line items is a combination of invoice ID and invoice sequence. Okay, so this is invoice sequence being something like line number. Okay, so because this primary key is a multi-column primary key, it can only be expressed at the table level. Make sense? I hope it does. Okay. So what about foreign key constraints? How do we express them? Well, it turns out that depending upon the nature of the foreign key that we're defining on our table, that's going to point to another table, to the primary key in that table. Depending upon its nature, we can either do it in line at the column level or at the bottom at the table level. Okay, so here we go. We're saying that we have a vendor ID in table invoices. It has a column vendor ID. It's an int. It references vendors. That's the table that we're pointing to. And then the field or the column on that table that we're pointing to is vendor ID. Now, this makes a lot of sense because typically, not all the time, but typically, the name of the foreign key field, the foreign key column, and the name of the primary key column are the same. Okay, that makes them easy to match up. Okay, so we can do it. I typically say in line. We can do it as part of the column and definition, provided that it's a key that's made up of only one column. Okay, because when you do this, when you say references vendors, when you say this, you can only identify a single column that you're pointing to. Well, what if you're trying to have a foreign key that points to a primary key that's a multi-column key? Well, you can't do it like this. Okay, you have to do it at the end of the table, at the table level. What does that look like? Well, let's go see. So we do have a table that has a multi-column primary key. We just saw it defined. It is well, no, we didn't do. So we just saw one that we could only do that way, and that's invoice line items. So if we wanted to point to invoice line items, of course, we could only do that with a table level foreign key constraint. But what we're showing here back on slide number 14 is we're coding a foreign key constraint between invoices and vendors where the foreign key is the vendor ID on invoices and it references vendors vendor ID. Now, why did we do this at the table level rather than at the column level? Here it was a stylistic choice because it was for a single column. We could have done it either way. The only time you're forced is where it's a multi-column key. All right. All right. So as soon as we create foreign key constraints, and we've been dealing with this kind of earlier in the course. As soon as we create foreign key constraints, we've told the server that we wanted to enforce the constraints, right? So that means that if we go to do inserts or updates or deletes, if we try to change the content in the database, it's going to remember the constraint rules. And if we try to break the rules with the insert or the update or the delete, it, it's going to fail that statement because it's breaking the rules of referential integrity. So here's a case where we're doing an insert into invoices and the values are 111. Well, let's look back. We're on slide number 15. Let's look back at the last time we did invoices. Well, it's right here. So we're invoice ID 1, vendor ID 1, invoice number 1, and it was the character 1. So, okay, that's fine. As long as we don't have an invoice ID 1, that's fine. That's going to work. The vendor ID 1 is only going to work if we have a row 1, a row in the vendors table that has a primary key equal to 1. If we don't, we're going to get the error that we have. So if we go back here, we say error code 1452 cannot add or update a child row. A foreign key constraint fails. So it's saying it's invoices, constraint invoices FK vendors, foreign key vendor ID, references vendors vendor ID. So I can only assume from that it went to the vendors table and it didn't find an entry for vendor 1. Okay. And because the server is given the job of policing and enforcing referential integrity through enforcing these foreign key constraints, it's going to fail that insert. Okay, so here's a constraint that uses an on delete clause. Now, if we go back a slide or two, you see that as part of these foreign key constraints, one of the options is that we can say on delete cascade set null. Okay, now what does this mean? Okay, so we say constraint invoices FK vendors, okay, foreign key vendor ID references vendors vendor ID on delete cascade. Well, I'm going to say that this is a bad idea. And I'm going to talk about this practice as practically as I can, okay? There are some times when you're trying to delete kind of the parent, okay, that when you've deleted the parent, the children have no value, okay, and you just want to discard them. So hence on delete cascade. So let's talk about something that would make sense. Let's say we were doing e-commerce, right? And we had a customer on our site, and they had a shopping cart, and they were filling it up with purchases or selections for purchase. Okay, so we'd have a table shopping cart. Okay, and then we would have probably, and the shopping cart would have items, just like orders and items. right? And then we'd probably have an associative table in the middle called uh, a cart line or uh, shopping cart underscore items. Okay, so that's what would make the many-to-many work between shopping carts and items. Okay, so let's say we decide to delete the shopping cart. Do we care about the items that were in the shopping cart? We really don't. Okay, let's say although a lot of vendors will keep shopping cart information between visits to their site, the naive thing to do is just, if in fact you leave the site, they destroy the shopping cart. Okay, and if that's what they're going to do, if they destroy the cart, do we really want to keep the record of the items that were in the cart? No. Okay, so on the definition for the table that holds the shopping cart items, okay, we could say on delete cascade, which would be to say, if you delete the shopping cart, you can delete us too. So, uh, you delete row 25 from the shopping cart for shopping cart 25, and then we have, say, 5 or 6 entries in the shopping cart items table for shopping cart 25. We'll get rid of them too. Okay, that's perfect. Here, I'm going to tell you why this is a bad idea. Okay, um, we have a bunch of invoices for. So this is a foreign key from invoices to vendors. Okay, so let's say we have 10 invoices for vendor 35. Okay. And let's say that somebody tries to delete vendor 35. Okay. Do we want to delete the invoices? Well, if in fact we've put all those in there erroneously, yeah, we probably want to. But the general case is, even if you get rid of the vendor, if these are actual invoices that you've got to pay, you don't want things that you have to pay kind of going away automatically. You don't want those 10 invoices just to disappear when the vendor goes away. What you would like to see is you don't want this clause in this particular case, because what you want to happen is when you delete the vendor, it's going to say you can't delete the vendor because it has invoices. And so if you really want to delete the vendor, well, go and delete each of the invoices individually, or you could do a delete that said you want to delete all of the invoices for vendor 35. Then you can go back and delete vendor 35. So this is, I think, an interesting feature in very limited circumstances, like the shopping cart. Okay, and this is a bad example of when you might want to do it. Okay, so forewarned is forearmed. Okay. So terms to know about constraints. A column level constraints are uh, they're expressed as attributes. They're right on the line where you define the column. Table level constraints are defined in their own line at the bottom of the definition in the table after you've defined all the columns. Why do you choose one or the other? Well, if the constraints are based upon a single column, it's really a style choice. If the constraints are based on multi-column keys, then the only way to do them is at the table level. The not null constraint, that's going to prevent you from inserting a row in which the value for that column is a null. This is important because so many times people don't know what null actually means. Does it mean that we know that this instant uh, doesn't have that value? It doesn't apply to this one? Does it mean that we don't know what the value is? Does it mean that we knew what the value was, but we accidentally forgot to key it in? Okay, so nulls are a slippery slope, so this is a popular constraint. The unique constraint um, uh, says this is a column that's not going to be the primary key. The primary key is unique implicitly. Okay, so this is a non-primary key column that we want to keep unique. And a really popular use of this is in a lookup table. We have a primary key, and then we have a name or a description or something like that. Uh, we don't want that to be null, and we want it to be unique. Okay. Why is that? We want to control values. That's the relational way. A primary key constraint will make a column or a combination of columns a primary key, and a foreign key constraint will make a column or a combination of columns a foreign key. Okay, syntax for modifying the columns of a table. Great idea. But before we do this, let's think about the use case for this. Okay? Um, this is a good time to talk about how you're going to write the script for the schema. Okay? Are you going to do it by hand? Or are you going to use a diagrammer that generates a script for you? You're going to have both alternatives available to you. So, um, so here's the issue. I think you have to ask yourself, what's your use case here? You know, you can change columns in tables. So you can add a column. You can drop a column. You can modify a column. You can rename a column. Okay? But you can also drop the entire database and redefine the table again if you're still in the database design phase. Okay? So, what's your workflow going to be, right? The workflow that I recommend for our final project in my course is that you, whenever you discover that you have the schema wrong, that you go back and you change your, if you're doing the schema script by hand, you go back and you change your schema script and you run it again. Okay. And the first thing you do in it is you drop that database and you define it all over again. Likewise, if you're working with the diagrammer, okay, in Workbench, and you decide, well, you know, I missed a column, or I put the column I called the column the wrong thing, or I gave it the wrong attributes. I'm going to have you go back and change the diagram and do forward engineering again and start further back in the workflow. Okay. If you're doing that at the beginning of a project when you are defining the schema, you won't get a lot of use for alter table. Okay. Alter table is useful when you actually have a database in production. Okay. And now you want to add a column to it. Okay. Or you want to change the definition. For instance, you might want to modify a column that let's say it's a varchar 20, and you're realizing that you really need it to be a varchar 45. Well, that would be an interesting kind of change if you thought to go through and you modify the column from a varchar 20 to a varchar 45. Well, that's going to work just fine because all the values you have in there already are going to fit in the new definition. Okay. It is hard to go and say you want to modify a column and turn a varchar 45 into a varchar 20. Okay, it will try to do it until it finds a value that's too long, in which case it will quit. Okay, so I think that you ought to think of this alter table as something that you're going to use when you're doing conversions. You have a database, you've got real production data in it. You either need to add a column or drop a column or change a column, in which case the considerations that you're thinking of are conversion considerations, okay? If you're in the beginning and you're in the database design, I say don't fool with the alter table. Go back and change the schema that you're either coding by hand or you're using the diagrammer to forward engineer into a program generated script, and then just load your data up and get started again. Okay? So what can you do? You can add, you can drop, you can modify, and you can rename. Let's take a look at those. So here's a statement that adds a new column. Alter table vendors, add last transaction date, which is going to be have a data type of date. A statement that drops a column. Alter table vendors, drop column last transaction date. Again, if we actually have a data in last transaction date, the server is going to complain. Okay, why? Because it's going to be deleting column values. Okay, there are ways to deal with that, but you have to consider that. Here's a statement that changes the length of a column. Alter table vendors, modify vendor name, varchar 100 not null. Well, before it was varchar something smaller than 100, I think. Let's go back. We're on slide 20. Table vendors. Let's find it. Where's vendors? We'll find it. Vendor name, varchar 50. So we made it bigger. Okay. Just like I said. Okay. A statement changes the type of a column. Now we're going to modify the vendor name to char 100, not null. Okay, that's fine, because that's bigger than varchar 50. Okay. Here's the statement that changes the default value. So we're going to change it to varchar 100 not null, default new vendor. Okay, that'll probably work. Here's a statement that changes the name of a column. So rename column vendor name to vname. Okay, not a well-chosen name, but I think that would work. Finally, a statement that fails because it would lose data. Alter table vendors, modify vname varchar 10 not null. Why is that not going to work? Well, let's assume that we haven't done all these interim things and it's currently at varchar 50. Okay, it's going to go through and it's row by row to convert them. And as soon as it comes to a row that has a vendor name longer than 10, it's going to stop and it's going to uh, tell you. So this says here, error code 1265, data truncated for column vname at row 1. So row 1 didn't even fit. Okay. So these alter tables are good for conversions. And you have to remember that if you're going from a longer definition or a value that holds more possible values to a shorter or fewer possible values, it will run a conversion. And if it finds a value that won't fit, you're going to get this kind of error. Okay? This is an error that happened at the very beginning of an attempted conversion. All right? Good. Now we can modify the constraints as well. So we can add a primary key. We can add a foreign key constraint. We can drop a primary key constraint. We can drop a foreign key constraint. Okay? And again, think of the two cases. One, we're in the beginning, all right, and we don't have the design of the database quite right. I'm going to say back up and get it right in whatever you're using to author the schema script and then start again. Or we could be pretty far along in a production database, in which case you can do these things, but you have to know that they're going to potentially trigger a conversion. So for instance, if you add a primary key or you add a foreign key constraint, primarily the foreign key, but it's going to do a couple things. One, it's going to build the constraint, but then it's going to go build indexes. Okay, so implicit in these adds in particular are conversions, and drops conversions that are potentially destructive. Okay. So adding a foreign key constraint, alter table vendors, add a primary key vendor ID. I guess we forgot it. One that adds a foreign key constraint. Alter table invoices, add constraint invoices, FK vendors, foreign key vendor ID, references vendors, vendor ID. Is it possible that we forgot it? Okay. We can drop a primary key constraint. So we say alter table vendors. Interestingly, we just say drop primary key. We don't have to identify the primary key because there is only one. Okay. Later, if we're trying to drop a foreign key constraint, we can say drop foreign key, and then we use the name right there. We can rename tables. So rename table vendors to vendor. Well, you already know from prior chapters that I prefer tables that are named in the singular. So I, of course, would like that. We can truncate a table. What's that? Well, essentially, we are deleting all the rows in the table. So it's less severe than a drop. If we drop a table, we delete all the data and also the schema definition. Okay, it's just gone completely. If we truncate a table, we delete all the data, but we leave the definition intact. Okay, this is the kind of thing that you might do. Oh, well, I'll tell you when I do it. I've been developing and testing a system, and I've got a lot of test data in the database, and now I want to move into production, so I want to get rid of the test data values, but I don't want to interfere with the definitions of the tables in the database, so I'll go to the tables that have transactional data, and I'll truncate them. Okay, so uh, and then I'll begin to use the system for production. Okay, a statement that deletes a table from the current database, drop table vendor. Everything's gone. The data's gone, the definition's gone, it's gone. Okay? Um, so when you say drop table vendor, like we just did, okay, uh, it's going to try to drop the table in the current database that we're using. What if we wanted to drop a table in a database that we're not currently using? Well, we would prefix it with a database or a schema name. That's that EX dot right there. Okay, here's a statement that returns an error due to a foreign key reference. Okay, we drop table vendors. Well, in this AP database, the invoices table has a foreign key constraint that each invoice is pointing to a row in the vendor's database, right? So, uh, can we just go drop the vendor's database? No, we can't. If we still have rows in the invoice database, they're all pointing to rows in the vendor's database. So we already know that we can't delete a row for an individual vendor if there are invoices that are pointing to it. Well, that goes for the whole table. We can't blow away the whole table and implicitly all the rows in it, as long as there are rows that are pointing to rows in the vendor's database from the invoices database. Well, then how would you do that? Well, you would delete the invoices database first. You drop that first, then you would drop vendors. Okay, so if you have to drop a bunch of tables, you need to drop them in order of how they point to each other, or sort of in the reverse order of how they point to each other, such that you're never trying to drop a table that's got rows and other tables that are pointing to it. Okay? Okay, now we're going to talk about creating indexes. And I can't emphasize enough that for MySQL and for most relational database products, um, a lot of the indexes are created automatically. So when you define a primary key, you automatically get created for you a primary key index. If you define a foreign key constraint, you automatically get a foreign key index. If you define a unique constraint, you automatically get a unique index. So what are we doing here? Well, we are creating further indexes beyond the ones that are automatically created for us on the basis of the constraints that we set up for primary keys, foreign keys, and unique constraints. Okay? So, how do we do that? Well, we either say create index name, or we say create unique index name on, and then the name of the table. Perhaps we want to prefix it if it's not in the current database. And then we identify the columns and whether they're going to be ascending or descending in the index. The default is ascending. Okay, so if they're not descending, we don't need to say ascending. Okay, so let's look at this. Create index invoice date index on invoice date. So this creates an index on invoice date in the invoices table. This makes it a lot easier to either sort, that is, order by invoice date, or to do a join on invoice date. Okay, so that would speed up the processing for either of those. We don't say ascending because that's the default. A statement that creates an index based on two columns. So we say create index invoices, vendor ID invoice number, IX for index, on invoices, vendor ID, comma, invoice number. And again, that might be that we're pretty frequently doing order bys that put them into that order. It could also be that we're using those two columns in joins frequently. Here's a statement that creates a unique index. So create unique index vendors vendor phone IX on vendors vendor phone. Okay. The other thing that we could have just said is when we declared vendor phone, the vendor phone column, we could have used the keyword unique just as an attribute on that column. Here's a statement that creates an index that's sorted in descending order. So it's on invoice total of invoices, and we want it to be descending. Now, why would we do that? Well, perhaps we sort a lot of things into descending order of invoice total. So that would speed up those sorts or order bys. And here's a system that drops an index, drop index vendors phone IX on vendors. Okay. And I can't emphasize enough, these are further indexes. Okay. So these are all indexes that are not being built by default on the basis of declaring a primary key or declaring a foreign key constraint or declaring a unique constraint. Okay, so these are further indexes. Okay, so now here's a script that creates the AP database, or at least part one of it. Okay, and you've probably seen this. I mean, we've been using these in our course to create the databases that came with the book. So when Joel Murach designed the database, whether he did it by hand, in which case he coded all this by hand, or whether he used a tool like the Workbench diagrammer, and then did forward engineering, the result either way was the script that when you run it will create the AP database. Okay, so I'm going to leave you to read through that. This has got 4 parts because it's on 4 slides. Okay. right there. Okay, now something to know is that, and I think I've actually shown this during other lectures or during class time, is when we go to Workbench, okay, and we go over in this panel and we navigate to a particular database and then we open the list of tables, right? And if we hover over one of the tables and we go over to the right, we have three icons. It's like an information icon, then there's like a wrench icon for settings, and then there's a grid icon for data. When you click the middle one, the wrench icon, this is what you see, okay? So these are the settings for that table, okay? And what this really is a graphical presentation of all the features we just saw, okay? Now, along the bottom, you can click on columns. That's what we're looking at now. Indexes, foreign keys, triggers, partitioning, or options. Now, in my class, we use columns, indexes, and foreign keys, but we don't use the last three. So we're going to look at the first three. So if you click on columns, here's where you can see what the columns are. You can see the order that they are defined in. You can see the data type, and you can see some of the attributes. PK for primary key, NN for not null, UQ for unique, B for binary, UN I think is unsigned, ZF is zero fill, AI is auto increment, and G, I forget what G is. I don't know the answer to that. Okay. And now one of the things that's kind of confusing is if you pick something to be a primary key, implicitly it's not null and unique. You don't always see those boxes checked. Okay, but you can rely on the fact that if you mark something as a primary key, it is implicitly not null and unique, regardless of how the boxes are checked on that row. Okay. All right, so that's the columns. Let's go to look at the indexes. Okay, so for every index that was either automatically generated or that we asked for specifically, we'll have a row here on indexes. Okay, and we can see that we have a foreign key index between invoices and vendors. That came from a foreign key constraint. We have a foreign key index between invoices and terms. That came from a foreign key constraint. And then we have invoice date, which is a further index that we defined explicitly in the AP schema script. Okay, and you can click on each one of these and you can see further details over on the right hand side. And then foreign keys. So you can see that this table has two foreign key constraints. One's on terms and the other's on vendors. And if you highlight the constraint, you'll see the details on the right-hand side. And as I said, we don't really work with, in this class, triggers, partitioning, or options. Character sets. Character sets are interesting, okay? um, the three that we talk about here are Latin 1, um, an older variant of UTF-8 called MB3, and a newer variant called MB4. Okay. Um, Latin 1 includes um, the characters that are used in American English, uh, British English, a lot of European languages. Okay. Um, that's a pretty small range when it comes to characters used in languages all over the world. Uh, UTF-8 is part of the Unicode standard, and it's the goal of the Unicode standard to be able to represent the characters used in all the languages all over the world. Excuse me. Um, so, uh, why are there two versions? Well, MB stands for multi-byte. Okay. It turns out that because a byte can only have 256 different combinations of its bits, um, that you can only represent 256 possible characters in one byte. So uh, the Latin 1 character set is a single byte uh, encoding. Okay. Whereas UTF-8 is part of Unicode. One of the reasons that Unicode can represent so many characters is it uses multiple bytes to encode some of the characters. So UTF-8 used uh, up to 3 bytes. I'm sorry, UTF-8 MB3 used up to 3 bytes. UTF-8 MB4 uses up to 4 bytes. It turns out that uh, the 3 byte version is kind of cheaping out. Um, it doesn't include all of the characters in the Chinese language. It doesn't include what people in the US are getting interested in a lot, like emojis. Okay, so if in fact you're doing some kind of social media site where people can use emojis, and people feel free to use them in all kinds of writing these days, uh, they can't be encoded in UTF-MB3. They can be encoded in UTF-8 MB4. So when we went to MySQL 8, a decision was made to bite the bullet and make UTF-8 MB4 the default. And so now it's truly an encoding that can support all of the characters that are part of the Unicode system, including Chinese characters and emojis. So that's why we use UTF-8 MB4 now, and that is new as of MySQL 8. Okay, so each of the character sets has a set of collations that can be used to sort them into order. Okay. And for the Latin 1 character set, which we're only so interested in because it's not what we're generally going to be using, there is a Swedish case insensitive collation, a general case insensitive collation, a general case sensitive collation, and binary collation. Okay, so the binary is interesting to read about. I'm not going to recommend that you choose it. Um, the thing is the language that you have Swedish or not? Okay, if it's not Swedish, then you probably want one of the generals. And the thing is, but you want the sorting to differentiate between upper and lower case. If you don't want it to differentiate, you want case insensitive. If you do want it to differentiate, then you want case sensitive. Okay, but for the most part, we're not going to be fooling with Latin 1. UTF-8. Okay, so there is a UTF-8 general case insensitive, Unicode case insensitive, Spanish case insensitive, and then binary. Okay, and then there are more specific uh, Unicode collating sequences. Uh, so this UTF-8 one works for UTF-8 MB3. UTF-8 is has been a synonym for UTF-8 MB3 in MySQL for quite some time. Whereas if you're using UTF-8 MB4, which is the default now, you're either going to choose, you probably won't fool with the bin, okay? We have AICI, which is accent insensitive, case insensitive. And then we have ASCS, accent sensitive, case sensitive. I believe that the default on our machines in our course is the first one, accent insensitive, case insensitive. We're going to do, we're going to take a look at that in a minute and we'll see what it is. So if the name ends with CI, the collation is case insensitive. If it ends with CS, it's case sensitive. If it includes AI, it's accent insensitive. There's the like accent aigu, accent grave, the umlaut, all those things. Um, if it has AS, it's accent sensitive. If it ends with bin, then the collation is binary. And again, the binary collating sequences are kind of technical, and I'm going to leave those for you to read on your own. Okay, now how would you view all the available character sets on your server? Uh, well, you could say show char set. Now, I'm not going to do all these in um, Workbench, but I am going to fire up Workbench here. And I'm going to bring it over, and we're going to look at a couple of these. Okay, so I'm going to get the local instance going, and I was already doing this, so that's how you can see that. So what's the first? Oh, I'm sorry. Here we are. So show char set. So this is going to show all the char sets. So let's go and take a look at Workbench. Okay. Say show char set and give it a run. And we're going to see all the char sets that are here. Quite a few. Okay, including UTF-8. And what is interesting is UTF-8 and UTF-8 MB3 are expressed as UTF-8, and UTF-8 MB4 is called UTF-8 MB4. And what's the default collation? Accent insensitive, case insensitive. Pretty cool, huh? Uh, and what's the max length of a character? 4 bytes. Now, why were they using just the plain old UTF-8 or which was the alias of UTF-8 MB3 before? Well, because it had a maximum length of 3 bytes. It turns out to not have been a well-made decision, so that's why we're using MB4 now. Okay, so that was show char set. What else can we do? Well, we can also say show char set like UTF-8 MB4. So let's see what that does. We're just going to put that there, and I think we're just going to see our one row. Okay, so we could do things like that. So one of the nice things about MySQL and really most of the implementations of SQL is that they eat their own dog food. So there is a database that has all the system tables in it. That is a MySQL database. And that's why we can display easily all the things that we were able to display. Okay, so that's the char sets. How to view all the available collations? Well, you can say what's kind of interesting here is I think we wanted to say show collation. Let's see if that works. Because we showed a char set and it didn't really look like that. So let's say show collation. All right, and do this. Yeah, and there they are there. So that slide should really say show collation. And this should say show collation. Oh, how do we view the available collations for a specific character set? Well, we could say show collations. No, we probably would say show collations like UTF-8 MB4. So let's try that. I think that was a typo. So show collations like UTF-8 MB4. Let's see. Maybe it's collation. Show collation like that. Let's see if that'll work. No, we're going to have to put that into apostrophes. Let's try that. UTF-8 and MB4. Well, that didn't work. Let's say show char set. Char set like UTF-8 and MB4. Let's see if it does actually work that way. No, we only get that one. Okay. Well, that doesn't work. Very interesting. All right. How do we view the default character set for a server? Show variables like character set server. This is going to be, for ours, it's going to be UTF-8 MB4, but let's go prove that. So let's just do that. And we're going to say the character set server is UTF-8 MB4. That's the default for the current default installation for MySQL, which is what we use in this class, is UTF-8 MB4. Okay, very good. And if we want to see what the default collation is, we can say show variables like collation server, the character set, show variables like a character set database, how to view the default collation for a database, show variables like a collation database. Okay, so you can get it for a particular database with this. Okay. How to view the character set and collation for all tables in a database. So select table name, table. Let's just do this. Let's just run this on our own. Okay, that'll make it fun. All right, so let's bring this over here. We have the AP database, so we want the table name, table collation from information schema.tables. That's where all this stuff is coming from, where table schema equals AP. And there we go. So we can see that where the collation we have for all those is UTF-8, MB4, accent insensitive, case insensitive. Okay, that's what we've got. Very nice. What else have we got here? A couple more things. How do we specify a character set and a collation? Well, we say we want a character set and a collation. So we say the keywords are char set and collate. Okay. So how do you do it for a new database? Well, we say create a database, name of the database, and then we can say char set name, collate, collation name. Ooh, I'm sorry. For an existing database, can we do this for an existing database? Yeah, we say alter a database, AR, and do this. I just want to point out this is going to cause a conversion to happen. Okay, maybe you're going to want to have backed up the database before you do that. I know I would have.